So for day 2's pre-lecture video, I am going to do a derivation of an expression that we see in this chapter. Doing the derivation in the pre-lecture video will allow us more time to focus on problems and concepts in class. So we're going to look at the expression for the speed of a wave on a string. One of the things that speed depends on is the mass distribution of the string, which is the mass per unit length. And also we're going to see will depend on the force that is applied to the string, which is basically then the tension that we have in the string. In the top picture, we see the string is in equilibrium, and there's a tension applied to it to keep the string in a horizontal position. In this situation, we're more or less neglecting the weight is not going to be pulling down on the string. And what is going to happen in order to start a wave on the string is you have to apply a vertical force, and we're going to call that F sub y, is the vertical force. And we apply the vertical force at one end of the string, which is going to, of course, cause that string to start moving upward. The speed that the string moves upward with is going to be called V sub y. And what happens is you end up getting, this pulling upward is really the disturbance that is going to cause the wave to travel through the string. As time goes on, more and more the string, of course, is going to be displaced. We have a point P located right here. Notice the point P is the dividing point between the portion of the string that is displaced and the portion of the string that is not displaced. Sort of the dividing line between where the disturbance has reached and where it has not reached. The speed that point P moves to the right with is also going to be the speed of the wave, the speed that the disturbance propagates with. Now, when we're applying the force to the string, we're applying an impulse. And let's review the impulse-momentum relationship that we learned in the previous semester. We know that impulse is a force times a time, and that gives us a change in momentum. The string wasn't moving before, so the momentum of the string is the mass that is moving times its velocity, and that's the V sub y. V sub y is a constant. And you might ask, well, as time goes on, that of course would mean that there's a greater impulse. So how do we get a greater change in momentum if the velocity remains constant? And the answer to that is that as t increases, so does the mass that is moving. So it's the m that is increasing in this expression as t goes up. All right, so what we want to do is we need to sort of figure out how to include the velocity of the wave, the speed that point P is moving with. And so what we're going to do is we're going to look at two triangles in this picture. We have the triangle here that deals with the vertical force and the horizontal force applied to the string. But we also have this triangle right here that deals with, the amount of string that's been displaced and how much the end of the string has moved up. Both of these triangles are similar triangles. And so what we know about similar triangles is that their sides are proportional in length. And so if we make the ratio of Fy to F, this should correspond to the corresponding sides of the larger triangle, which would be v sub y times time times v times time. And if we rearrange this, we can see that this will give us a relationship between the force that's applied vertically, force sub y, and the different velocities and the horizontal force. And we're going to use this later. So if we go back to our impulse-momentum relationship looked like this. And from our previous slide, remember f sub y was equal to f times v sub y over v. So we're going to substitute this into this expression. And we notice that the v sub y then is on both sides, so that can be canceled. And the mass we can use would be equal to the mass per unit length times the length of the string, which would be v times t. This is the length right here. So if I do some substitutions, I have f times t over v equals mu v times t. And notice now time is going to disappear. And I can actually then, I'll do one more thing, f equals mu v squared. So v could be written as the square root of force over mu, taking the square root. And that's the expression for the speed of a wave on the string. So we found that this expression here, we sort of derived it using some pretty simple physics. And if we think about it, the relationship does make sense that the velocity is proportional to the tension, that how fast it's going to go depends on how responsive the string is to it. But it also makes some sense that the mass is going to have sort of an inverse relationship, because the mass is going to be like the inertia, the resistance to the motion. And so even thinking about it in very simple physics sense also helps us make some sense of it.